Today we are starting a new chapter. In chapter 3, we will be discussing what the derivative can tell us about a function. And we'll use those ideas to solve a brand new type of problem, the problem of optimization, which is trying to find out the maximum or minimum values of a function. But before we can get into that, the first thing we're going to discuss in this section is when and where a function is increasing or decreasing. These terms of increasing and decreasing should be fairly intuitive, but we will actually give them formal definitions anyways. We say that a function f is increasing specifically, we don't say at a point. We specifically have to talk about increasing on some interval, usually going to be an open interval. So f is going to be increasing on an interval a to b if when x1 and x2 are in a and b, x1 less than x2 implies that f of x1 is less than f of x2. So basically, if we put smaller values into our function, we get smaller values out. Bigger values give us bigger values. This is what we expect to have from something that's increasing. The bigger the thing we put in, the bigger the value we should get out. Decreasing is pretty much the opposite. So I basically copy over that definition, but instead of having increasing here, it's going to be decreasing. And instead of having f of x1 is less than f of x2, it's going to be greater. Basically, if we put smaller numbers in, we're going to get bigger numbers out. And vice versa. If we put bigger numbers in, we're going to get smaller values out. Note that a function can be increasing in one interval, but decreasing on another one. Let's take for an example our pretty standard first example for a lot of things, something that's more complicated than a line, but fairly simple, our familiar parabola, the x squared function. If we were to graph that function, we already know it looks like this. Let me make that color a little bit, stand out a little bit better. I'm not supposed to actually hit the origin, but it's the idea that counts. If we put in values that are, or x values that are positive, so say from 1 to 2, or even from all the way from 0 to infinity, we would expect this function to be increasing on that interval. But on the other side, when we're talking about negative x values, we expect our function to be decreasing. It's going down. When we put in bigger numbers, so less negative numbers, you could say, we get smaller values out. Here, when we put in bigger numbers, we get bigger values of x squared. So you'd say here it's increasing on the interval from 0 to infinity, and it's decreasing on the interval from negative infinity to 0. Now, one other thing that we have in this, instead of having something be increasing or decreasing, we can also have a function be constant. Basically, we're saying that if a function it just takes on the same value for every point in that interval, it's said to be constant on that interval. Now, we're not actually going to run into too many functions where we do have intervals where a function is constant. It is important to include this as a possibility, but anytime a function is going to be constant, it's either going to be constant everywhere, just like y equals 2 is a constant function. It's not increasing or decreasing anywhere. It's always constant. Or it's going to be a piecewise function, where we define it by one formula for one part and another formula for another part. But we're going to include it here because we want to be able to talk about constant functions as well. So how do we determine where a function is increasing, decreasing, or constant? I mean, with our parabola, we were kind of able to just use the intuitive idea that we have about what increasing or decreasing means in order to just kind of reason it out. But sometimes we don't have the graph in front of us. Sometimes it's a little bit more complicated than that. Sometimes graphs can be deceptive. So we want to be a little bit more precise about how we find out where these things are actually increasing or decreasing. We're going to use calculus. Specifically, the derivative is going to tell us the answer that we want. We have a theorem. So we're going to have a function f is differentiable. That just means that the derivative even exists. If the derivative doesn't exist, of course, nothing here is actually going to be relevant, because we're going to be using the derivative to actually solve the problem. So if we have a function that is differentiable on an interval a to b, we have three situations. If the derivative of f is positive for all x in ab, then f is increasing. Specifically on ab. If the derivative is negative for all x in the interval, then f is decreasing. And finally, if the derivative of f is 0 for all x in the interval, then f is constant. Now notice that when we're saying that when the derivative is equal to 0, we have to be talking about the entire interval all at once. If we're not talking about entire interval points, then we might not be constant at that point. If we have a function that is, say, the derivative is positive except for one place where it's equal to 0, it could still actually be increasing that whole time. We'll see how all that works as we go through this. Now, it should be fairly easy to see exactly why this is true. Think about some function that we have. We have something going on like this. What does it mean to have a positive derivative? So say at this point here, would the derivative be positive or negative? Well, it'd be positive because the slope of our tangent line is positive. Remember, a positive slope means that you're starting low and moving high. That's corresponding to where the function is moving upwards. So we'd expect the function to be increasing at that, well, not necessarily at that point, because we're not talking about increasing at a point, but we'd be expecting it to be increasing in an interval around that point. Same thing with the derivative being negative. So over here, we'd expect our tangent line to have a negative slope. And so that kind of agrees with the fact that on this part, the function is moving downwards, that it is decreasing on that part. Now, if we were to include something where the function becomes constant, say it gets up to this point but then kind of flattens out, points over here have a horizontal tangent line. They have a slope of 0 for the tangent line. And so that's why when the derivative equals 0 for an interval, we end up with a constant function. It corresponds to those horizontal tangent lines. We can go back to the function f of x equals x squared. Recall that our derivative of x squared is just a 2x. If we put in, say, values in 0 to infinity, we're putting positive values into 2x. Of course, the 2 doesn't change that sign. If we put a positive value in here, we get a positive number out. And therefore, on the interval from 0 to infinity, the derivative is always positive. It corresponds to it being increasing, the original function x squared being increasing from 0 to infinity. On negative infinity to 0, there we're putting negative numbers into 2x. We get negative numbers out, and that corresponds, so the derivative being negative there corresponds to the original function being decreasing there. So what do you do if I just give you a function and I ask you to determine where it is increasing, decreasing, or constant? From the theorem, we do want to determine where the derivative is positive, negative, or 0. But we want to be pretty precise about it. How do we tell where a function is positive, negative, or 0? If I gave you a function, let's say let's say it this way. Where is f positive, negative, or 0? How can we determine that if I just gave you an arbitrary function? Well, we have one little fact that can help us here. If f is continuous, and we want to say where does it change between positive and negative, let's kind of look at a graph here. Let's say we have some function here that is positive here and negative here. What has to happen in the middle? Well, if it's continuous, I have to hit somewhere. So continuity does tell us that in order to change from being positive to negative, we have to hit 0 at some point. Or the other way around. If I started at negative and went positive, I'd still have to hit 0 somewhere. So the only way that I can switch between positive and negative is either the function hitting 0 or if the function is not continuous. Because it could be possible that we have a function that starts down here and then kind of jumps up to here. That's a possibility. But we have to have some point of discontinuity, or we have to hit 0 somewhere. There's no other options. So in order to actually determine where a function is positive or negative or 0, is start with determining the points where the function is 0 or not continuous. And then we basically can put those onto a number line. Maybe it's the function is 0 here, but it's discontinuous here, and then becomes 0 here again. Maybe I can determine that at maybe some A, B, and C. Then I know on these intervals, if I determine every place where it equals 0 or is discontinuous, then I know on these intervals it's either always positive or always negative. There's no way it can switch in the interval from A to B from being positive to negative or vice versa, because I know there's no place where it equals 0 or the function is discontinuous in that interval. So that will allow me to say pick a test point. If I pick any number between A and B, put it into my function. So maybe I pick a test point, call it T, just for test. If I put T into F, and I find out, well, for that particular T that I picked from the interval A to B, I got a positive number, then I know every other point between A and B gives me a positive number when I plug it into F. And I can do that for each interval. Well, in our particular example, the particular problem that we're trying to apply this to, we're actually not looking at where is the original function positive, negative, or 0. though that can be sometimes be useful to be able to do that. But we're more concerned about where is the derivative positive, negative, 0. So essentially, we start with the question of where is f increasing or decreasing. This turns into the question of where is the derivative, where is f prime, positive or negative. And based off what we did on the previous page, this essentially turns into the question, where is f prime 0 or discontinuous? Because if we can determine where f prime is 0 or discontinuous, that will allow us to find out where f prime is positive or negative, and that essentially immediately tells us where f is increasing or decreasing. Now, in the case of talking about the derivatives can't ever be discontinuous except when the derivative simply doesn't exist. There's no time when you have a derivative that exists at a point, but it's discontinuous. So we can essentially, instead of saying discontinuous, we can essentially cross that out and just put does not exist. We're asking where is the derivative 0 or where does it not exist? We're going to give a name to the places where that happens. We're going to say if, let's say c is a number where, let's actually specify here, in the domain of f, where either f prime of c equals 0 or f prime of c does not exist, then c is a critical number, or something frequently also referred to as a critical point. Sometimes people will actually say that c comma whatever the y value at c is the critical point. We're not really going to make that distinction here, and the book just refers to them as critical numbers. I will probably, even if I wanted to stick with what the book did, I'll probably just accidentally use critical point most of the time. So I'm just going to use them interchangeably. The point here is the critical. We won't use critical for any other concept in this course. So a critical number or critical point of a function is a place where the derivative is either equal to 0 or does not exist. And being able to determine these critical points will help us to determine where the derivative is positive or negative, which will in turn allow us to determine where the original function is increasing or decreasing. The book breaks this down into a 4-step process. When we're asking whether or not a function is increasing or decreasing, or where it's increasing or decreasing, first thing we do is take the derivative. Then we go ahead and locate those critical points or critical numbers. Essentially, we're looking at we set f prime equal to 0, and we also ask ourselves, where does f prime not exist? What I like to do at this point is make a number line. Like I kind of showed before, where I basically just make a line with an arrow on it, just telling me that positives this way. I put all the critical points or critical numbers on that. So maybe this is a C, a D, an E, just go along with that. But we have those numbers came out of setting the derivative equal to 0, or the derivative not existing at those points. I would then go ahead and pick test points. In every single one of these intervals. And I will take those test points and I'll plug them into the derivative, specifically the derivative. Don't plug them back into the original function. Put them in the derivative. You will get either a positive number or a negative number. I mean, it can't be 0 and it can't be undefined because we've already determined the points where that happens. It'll have to be either positive or negative. And then when you determine whether or not it's positive or negative on those, that will tell you whether or not the function is increasing or decreasing. So maybe I took this test point and I found we got a positive number. I'll put a plus sign over that interval, telling me that from negative infinity to c, my function has a positive derivative, which means that it's an increasing function. Maybe we'll even go ahead. If we want, we could also be even a little bit more specific about that. Since it has positive derivative, maybe I'll go ahead and put a line like that, telling me that it's increasing. It's going upwards in that place. Maybe on this interval, it has a negative derivative, so the function is decreasing. Maybe it's still decreasing on this interval, but maybe it's increasing over here. I don't know. That's a possibility. But we're going to go through a number of examples and see how this works. Of course, this is kind of a schematic for what we're going to be doing. We're going to put this to work in various examples. Now, I will go ahead and move most of these problems on into the next video just because, I mean, I don't want to burden this down as one huge video. But because we're going to be going through a lot of examples, let's go through a few of the easier ones right now. We're going to start with problem 16. Here we have the function f of x is equal to 5 minus 3x. We have a linear function. Now, one thing that we might not have understood from this guideline here, part of our definition, here's our definition. Our definition of critical number or point does require that our c, our critical number, to be in the domain of f. So it can be very useful to determine what the domain of our function is right up at the beginning. What is the domain of this function? Now, this is a linear function. It's pretty simple. This domain is going to be all real numbers. There's no number that we can't plug into this function. And say all real numbers, or we can go ahead and we can use negative infinity to infinity. I'm going to keep talking about the domain for each of these problems. It won't really be relevant until some of the later ones. But I do want you to get into the habit of thinking about the domain when you tackle these kind of problems, because it is going to be kind of important later on. Our first step is to take the derivative. So the derivative of 5 minus 3x, the 5 goes away. It's just a constant, so it goes away. Minus 3x becomes a minus 3. So the derivative here is always equal to negative 3. Now, at this stage, we could think about what the critical numbers are, but the derivative always exists, and negative 3 is never equal to 0. So, really, we're just saying here that no matter what, our derivative is negative. It's always a negative 3. And so, all we're really saying here is that f is decreasing everywhere. Or decreasing on the interval negative infinity to infinity. If we want to stick with the interval notation here. And that should be relatively straightforward. If you think about it here, we have a line. That line is going to be it's going to have the form, so it goes through at 5, that's our y-intercept, and it has a slope of -3. And I completely missed that point. There we go. So it looks something like this. Not precisely, but close enough. It looks something like this. It is definitely decreasing everywhere. I guess we could go ahead and actually graph it. If we graphed our line, f of x equals 5 minus 3x, it's definitely decreasing everywhere. Let's look at another example that's not quite so straightforward, though. In problem 18, we have y is equal to negative 2x squared plus 8x. We have a quadratic. Of course, our domain, which I'm going to keep doing, it's going to be all real numbers, or negative infinity to infinity, because it's just a polynomial. All polynomials have domain all real numbers. We start with our derivative, the derivative of y. So negative 2 times the derivative of x squared. Derivative of x squared is 2x. So we're going to have a negative 2 times 2x, or negative 4x. The plus 8x just becomes a plus 8. We want to know from this, where does the derivative equal 0, or where does the derivative not exist? Now, in this particular case, again, our derivative is a polynomial. It always exists, so we don't really have to worry about that portion on this problem. But we do have to worry about when does the derivative equal 0. When is negative 4x plus 8 equal to 0? Well, we have to solve. I'm going to go ahead and bring the 4x to the other side, but I'm going to write it on this side of the equation. So basically, 4x has to equal 8, or in other words, x has to equal 2. That means we have a critical point. We have one critical point of x equals 2. And if we put that onto a number line, we just have a 2 here. But this represents that we have the intervals negative infinity to 2 and 2 to infinity. Those are two separate intervals to be working with. We're going to take test points in those two intervals. So from negative infinity to 2, I can pick any number that I want. I should get the same result of being positive or negative for any point in that interval. So pick the one that's the easiest. What would be a good number to pick between negative infinity and 2? Well, I might as well just go ahead and pick something like 0. 0 is always a good number to pick, as long as it's not one of our critical numbers. What is the derivative at 0? Because remember, we have to take our test points and plug them into the derivative. Well, we have negative 4 times 0, or 0, plus 8. Well, 8 is definitely a positive number. So over here, it's positive. Or in other words, it's increasing from negative infinity to 2. From 2 to infinity, I can take another point, another test point. Go ahead and pick the smallest one, or the smallest integer at least. I'll go ahead and pick 3, because it's easy enough. But it doesn't matter which point you pick in here, just pick whatever you find the easiest. Of course, then we're taking negative 4 times 3 plus 8. Negative 4 times 3 is a negative 12. Negative 12 plus 8 is a negative 4. Negative 4 is definitely a negative number. So over here, we have a negative derivative. So the derivative over here is positive. The derivative over here is negative. That means over here, it's increasing, or the original function is increasing. Over here, the original function is decreasing. So it's increasing from negative infinity to 2, and it's decreasing from 2 to infinity. If we go ahead and actually plot that function, so it was y equals -2 times x squared plus 8x, we can see that the point on here of 2 comma whatever the value of the function is at 2, which I guess is 8, that is actually the vertex of this parabola. That we have a name for it when it comes to parabolas. And we can definitely see from -infinity to 2, until we get to the x value of 2, we are increasing. It is going up. From 2 onward, from 2 to infinity, we are decreasing. It's going down from that point forward. And that agrees with what we got from our calculations. It increases until we get to x equals 2, and it decreases from that point forward. That's what we're determining in these problems. I'm going to leave the other problems to the next video, though. We'll see more complicated ones like higher powers and things that may not just be polynomials, stuff like that. And we'll see where we might run into some issues or some things that we have to think about. But I'm going to leave this video for here. So I'll see you in the next one.